Greetings everyone, and welcome to my next video on applied differential equations. Today we're looking at the theory behind solving homogeneous systems. So you can see I've already written out a bit. We're going to try to solve the vector x prime is equal to a vector x, where A is an n by n matrix. This is a homogeneous system, and the reason that you can tell that is that the non-homogeneous would actually have, for example, a little plus f of t here, where f of t is a vector, some function that doesn't contain x and y in it. It could have, it could be, e to the t's or sine of t's or something like that. And we're only going to be looking at the case where the derivative vector x is some matrix times the vector x itself. Using, of course, this terrible prime notation, which really means with respect to x, but we're going to take it with respect to t here. The general solution is that vector x is some is c1 x1, where x1 is a vector, plus c2 vector x2, plus c3 vector x3, all the way up to cn vector xn, where the n by n matrix in A corresponds to the number of terms in the solution, where all of these vectors x1, x2, x3 to xn are n linearly independent vectors. So what do we do with that? We're going to look at a method of solution. We look for vector x, so these little lowercase vectors that we want in our solution, is equal to some vector k times e to the lambda t. And let's just make a little note here. The interval of solution then is just negative infinity to infinity. We've got no division by zero problems or anything like that. And for a vector k not equal to the zero vector here, and some number lambda. But if vector x is equal to some vector k e to the lambda t, where k is not a function of t, then when we take the derivative x prime, the derivative k is just a bunch of constants. And so we're going to get k times the derivative of e to the lambda t. Lambda is also a constant, so we're just going to get a lambda out front, and we get e to the lambda t here. So we're going to plug this in. And I'm trying to make my capital X's really big and distinct from my lowercase x's. So our original matrix equation was vector x prime is equal to a vector x, where these are capital letters. Then what we found is that for each of these terms, if this is a sum, then lambda k e to the lambda t, where k is a vector. So each of these little vectors here is equal to the sum is equal to a times k e to the lambda t. And essentially what we've done here is we've said that instead of writing x as this huge sum, we're writing it instead as just the column vector k times e to the lambda t. Notice that the e to the lambda t's are going to cancel here. And then we get that lambda onto k is equal to a onto k. And if we take a look at this equation, this should look really familiar. What this implies is that for matrix A, lambda are the eigenvalues and k are all the eigenvectors. Remember what eigenvectors and eigenvalues are. That if I take a matrix A and I multiply it onto an eigenvector, then I just get a multiple of that vector. So if you take a look at this, there are four different cases. One, that when you find the eigenvalues and eigenvectors, you get distinct, real eigenvectors. So if it's a 2 by 2 matrix, you get two different eigenvalues. Don't know why I wrote vectors there. So if it's 2 by 2 matrix and you find the eigenvalues to be like 1 and 3, but you get two different ones, then when you find the eigenvectors, you're going to get two different eigenvectors as well. There's the second case, which is that you've got repeated lambda, so eigenvalues, with enough eigenvectors. What does enough mean? It means that the geometric multiplicity, let's actually write that out, geometric multiplicity is equal to the algebraic multiplicity. And so you'll recall that the multiplicity of an eigenvalue is the number of times that it occurs. So if you have, for example, a 3 by 3 matrix and you find that its eigenvalues are 1 and then 2 and 2, because when you solve, you get, lambda minus 2 all squared or something like that, then the 2 essentially appears twice and it's going to have an algebraic multiplicity of 2. Then the geometric multiplicity is the number of eigenvectors that are associated with that eigenvalue. And when you find that there's enough of those, then you'll have, for example, in a 3 by 3 matrix, when you do all the eigenvalues and eigenvectors, you're going to get 3 eigenvectors in total. And so that's all very convenient. But of course, then case number 3 is going to be repeated eigenvalues lambda with a geometric multiplicity less than the algebraic. And then case 4, just to make life complicated, we're going to get complex eigenvectors as well. So those are the 4 possibilities, and that's basically the theory behind solving homogeneous systems. In my next couple of videos, I'm going to do examples of each of these cases.